Yeah, so for just a second then, I'm kind of repeating myself or reviewing a little bit from what I did last time. But in 13.6, there's 2 or 3 or 4 really good ideas. And I had these notes down the other day. I might just do them again real quick. One idea is this thing called the Duf. It's called the Duf. That's a subscript right there. That's a subscript U. Actually, it's not called Duf, I just say that. It's D with a subscript U of f of xy. It's called the directional derivative. And the formula for it is the partial derivative with respect to x at the point xy times the u1 plus the partial derivative with respect to y times the u2, where, and that's it. And so what the heck is the u? The u is a little unit vector. And so this is this new thing, and like I said, I explained this pretty well in the last lecture, so I'm going to repeat myself just a little bit here, but this is the slope in it. It's called the directional derivative, but I'm going to call it the slope in any direction. It's the slope of the surface in any direction. You know, individually, these partial derivatives by themselves were slopes. The partial derivative with respect to x was the slope in the direction parallel to the positive x-axis. The partial derivative with respect to y was the slope in a direction parallel to the positive y-axis. So what we have now is this thing called the Duf, which is the slope in any direction. The direction is specified by the unit vector u. So you got to give me a point to, okay, you got to give me a surface, f of xy. You got to give me a point to stand on. Then you got to give me a direction to look in, and then I can calculate the slope in that direction. And what it is it's this formula. And because what it is it's sort of the slope in the x direction times how much you're looking in the x direction, the x component of the unit vector. And then it's the slope in the y direction, sort of multiplied by how much you're looking in the y direction, the y component of the unit vector. So it's sort of an averaging of these two slopes. We had these two slopes, now we use those two slopes to get the slope in any direction. I'm on a 3D surface, but this direction you make me look in is a 2D direction. That's a two-dimensional vector. So that's awesome. Now, guess what? So I can stand at this point and I can calculate that slope, that slope, that slope. I can calculate all these slopes, infinite slopes. Guess what? One of them might be the biggest slope. And the direction of the biggest slope is this thing. It's called the gradient. It's a vector. It's a vector, and what it is it's the partial derivative with respect to x at the point, comma, partial derivative with respect to y at the point. This is called the gradient. When you look in this direction, this is the direction of maximum slope. It's called the gradient. It is the direction of maximum slope. And then it turns out, if you calculate his magnitude, and so there's some proof for this stuff that I'm not doing. I'm just, you know, here I am sort of writing down formulas. But if you calculate his magnitude, then that is the maximum slope. And it's kind of a subtle distinction, but you know, the gradient is a vector. So sometimes people think the gradient is the slope. Well, technically, the gradient is a vector that points you in the direction of the maximum slope. The magnitude of the gradient is the maximum slope. The gradient is not the slope. The gradient is a direction of maximum slope. The magnitude of the gradient is the maximum slope. There's another big idea. So these are big ideas, the Duf and the gradient. You know, as a matter of fact, after you learn about the gradient, then I read this in the book. The book says, okay, there's an alternative definition of this Duf. They say you could think of it as the gradient dot product the unit vector. And that is true. You know, the gradient is a vector, partial derivative of x, partial derivative of y. The unit vector is a unit vector, u1, u2. And if you dot product those vectors, you know, you multiply the x components, you multiply the y components, and you add them up. That's the formula for the Duf. So you could think of it as that formula. So there's a lot of good questions, and there's actually another good idea about this gradient I might try to get to before I really finished with 13.6. But I think I want to do an example. So a classic example, and I actually did one the other day, but I'm doing another one. So this is a little bit of a repeat, but I'm gonna make up a surface. So I've got a surface. I'm making this up. 3x squared y squared minus 2x cubed y plus y squared minus 8. That's a surface. Let's say I am at the point -1, 2, and if I just plug those in real quick, I think it's 12. I just plug those in to get a z value. So this is a surface. I plugged in an x and a y value. I think that's the correct z value. It turns out what you'll discover in a lot of questions is the z value might not matter much, but I'm on a surface, I'm at a point, I sort of feel obligated to give you the z value. But now what do I do? What's the question? The question is, a bunch of questions. I want to know what is the slope of this surface in the direction of, and then I think I'll give you a vector, 4, 7. Here's another question, part B. What is the slope in the direction of direction of theta equals (150 degrees). Here's another question. Part C. Get rid of this little formula. Part C. Watch this. What is the slope of the surface in the direction? Watch this. In the direction of the point. This is kind of a funny way to word this. So I'm wording it. I got 3 questions that are asking you about slope. But I'm wording them 3 different ways. In the direction of the point, 0, 0. Okay. Fourth question, D. What is the maximum slope and the direction in which it occurs, and the direction in which it occurs? So this is pretty good stuff. I've got a surface. That's plenty of questions, by the way. That's enough questions. This looks a lot like a test question when we finally get around to taking a test. So look what I've done. I've asked you for a slope 3 times. Then this last question is different. This last question is about the maximum slope. You know, this last question is about the maximum slope. I think it has to do with the gradient. Okay, but we'll get there. I think the other ones are just about a slope. What's the slope? What's the slope? What's the slope? And I think slope is the Duf. It's called the directional derivative or the slope. And so they gave me a surface, they gave me a point, and they gave me a direction to look in. So I think I can do this. I think the answer to all three of these first questions, A, B, and C, I think the answer is going to be some number. 16, 12, negative 11, or, it's going to be a slope. Okay, so guess what? By the way, when in doubt on any of these questions, and you know because you have these formulas in front of you, but for all this, we're going to need partial derivatives. So step one, let's find some partial derivatives. So right up here, before I even do the work, I need fx in general, and I need fy in general. I need them in general, but then I do need them at this point also, is what. But let's start by getting to them in general. The partial derivative with respect to x. The partial derivative with respect to x. So x is the variable. Pretend y is a constant. And you want to talk to me? What do you think?
6x minus 6x.
6x, well, wait a minute. If this y is a constant, then and it's multiplied to constant, then it stays there. So it's 6x y squared. It stays there. It's a multiplied constant. Minus 6x squared y. Hey, this is not a multiplied constant. When I get over here, he's an added constant, and his derivative will be 0, and his derivative is 0. So we're done. That's the partial derivative with respect to x. All right, now hold on. Just switch gears if we can and do the partial derivative with respect to y. Okay, now y is the variable, x is a constant. So now
that's 6x squared y.
6x squared y, right. Y is the variable, 2x cubed is a constant. So negative 2x cubed is the derivative. Y is the variable, so 2y is the derivative. Okay, cool. Those are my two partial derivatives. They should be easy, but they take a little concentration to treat x like the variable and y constant and vice versa. I want to evaluate these at this point. I got a lot up here on the board, but the notation for that is, hang on. That I'm evaluating this partial derivative at the point negative 1, 2. So I'm plugging in the point negative 1, 2 into this partial derivative with respect to x, and it will be a number. What will it be? Negative 1, 2. I think I got negative 24 minus 12. So that's negative 36. It'd be nice if you double check me. And with respect to y, I'll kind of plug in the negative 1 and the 2. By the way, as you can tell, you don't need that z, You don't plug in the z. You need the x and the y to plug in. That's sort of what all these notes say over here. You're plugging in an x and a y into the partial derivative. You're plugging an x and a y into the partial derivative. That's what we're doing. We're evaluating this stuff at the point x, y. When I plug in the negative 1, 2 here, 12 plus 2 is 14 plus 4. I think I just got 18. He's negative 36 and he's 18, I think. Never made a mistake before, but I could today. Cool, dude, I'm ready for this. I'm ready for this. I want to do this. I want to do the slope in the direction. This is a Duf. I call it a Duf. It's a D with the subscript unit vector U of F. I'm just going to be a little sloppy here and call it the Duf. Here I go. What am I doing? It's this formula. It's the partial derivative with respect to x, negative 36, times the unit vector, the x component of the unit vector. Oops, guess what? I forgot to get myself a unit vector. I have a vector. This is a direction. I'm looking in the direction of 4, 7. That's, by the way, that's out 4 and over 7. That's roughly that direction. But to do the calculations of the formula, I need a unit vector. So I divide him by his own magnitude. The magnitude of this guy is 49 plus 16 in a square root, right, you guys? I was Pythagorean theorem champion in 2nd grade. So 16 plus 49 square rooted. I got that down. So the unit vector that we're talking about is this vector 4 over the square root of 65, comma 7 over the square root of 65. And anyway, I'm going to leave it like that. And what I need here is the x component of the unit vector, plus the partial derivative with respect to y at this point in this direction would require me to multiply by the y component of the unit vector. And so this is cool, you guys. That's a negative 72, or no, it's not. That's a negative 144 over the square root. That's 18 times 7, which is 126. Positive 126. This was negative 144. Positive 126. I think I'm getting negative 18 over the square root of 65. That's my slope. I should go back here and be a little less sloppy. This is my Duf evaluated at the point negative 1, 2. I mean, this is my Duf at any x, y. This is my Duf evaluated at the point negative 1, 2. Not only that, it's also in that specified direction. This is the Duf. With that unit vector, at this point, this is the slope. Hey, make that a decimal for me. Roughly, that's an 8. 18 over 8. 2 point.
You got negative 2.23.
Okay, thank you. So there it is. I like my exact answers, you guys, when I can get them. Sometimes you like to give me decimal answers, approximations, but cool. That was easy in a way, but it's new and different, but it's just a formula. By the way, you need to memorize these formulas. I think last chapter I gave you some formulas, but this time I'd like you to know these guys. And you were checking my math? I did everything good? Check. Okay, thank you. Hey, next question. It's another Duf. It's the same Duf. It's at the same point. It's the same surface. It's the same point, but it's a new direction. Now the direction is 150 degrees. By the way, when we give you an angle, that's measured in standard position, which means from the positive x-axis counterclockwise. So that is 90. That's about this way. By the way, the first slope I did was roughly that way. I'm waving here, but was roughly in that direction. Now this one is roughly in this direction. It's probably a different number. Who knows? It could be positive, it could be negative. What is the surface doing in this direction? By the way, back to this one. In this direction, what was the slope doing? Looks like it's not too bad, but it's decreasing at a rate of negative 2.23. I mean, if I was to take a step in that direction, I would fall 2.23 units. Of course, as soon as I take a step in that direction, I'm at a new point and my slope changes. But at this point, that's what I'm facing. Let's calculate it at 150 degrees. Now, how do you get a unit vector out of 150 degrees? I did say this in my notes Monday. If someone gives you an angle, your unit vector, when someone gives you an angle, this is always a unit vector. This should have been brought up in chapter 11. I'm not sure if it probably came up, but the cosine, the cosine of theta, comma, sine of theta is always a unit vector. Because what's the magnitude of this?
1.
It is 1. Because cos squared plus sine squared is a 1, square rooted is a 1. If I just do this magnitude for any theta, this is always a 1. This is always a unit vector. So given an angle, sometimes then this Duf formula looks a little different. In fact, the book sometimes gives you this formula like this. They call this the cos of theta, and they call this the sine of theta. But you're not always given an angle. That's why I wrote it another way. But here we go. This time we are given an angle. I'm ready. The Duf in this direction is, again, it's the negative 36, but this time it's times the cosine of 150. That's the x component of the unit vector, plus the 18, and times the sine of 150, because that's the that's the y component of the unit vector. Again, I like to do these numbers exactly. You guys sometimes punch it in your calculator. The cosine of 150 is over in quadrant 2. It's the negative square root of 3 over 2, I think. The sine of 150 is 1/2. So there I am. Sorry, I'm way down here at the bottom of the board. I'm gonna, but I can cancel that. That's 18 square roots of 3 plus 9. 18 square roots of 3 plus 9. Everything's positive. This is exact. I would like a decimal approximation again, please.
40.18.
Thank you. 40.18. 40.2, we'll call it. Dude, that's pretty steep. Okay, let's think about that one more time. Listen, it takes me a while to do these problems because I do like to talk a lot. Listen, I was standing at this point. I'm on this surface. I was looking in that direction and the slope was negative 2.23. I rotate over here and look in this direction and holy shit, the slope is 40. I mean, it's very steep in front of me in this direction. Over here, it's slightly falling. I mean, that's what's cool. At a point on a 3D surface, I can get all kinds of slopes depending on which direction I'm looking in. That's the point of this. I'm also, in case you noticed, you know, I asked this A, B, and C, which are all just Duf questions. Because I'm asking for a slope. I'm asking for a slope. I'm asking for a slope. But what I did to you on all three of these questions is I gave you the direction 3 different ways. The first time I gave you a vector. You had to make it a unit vector, but I gave you a vector. The next time I gave you an angle. You take the angle and you make a unit vector. This third time is funny. This third time I gave you a point. So I'm still, if you keep in mind, I'm still standing at this point, negative 1, 2, 12, but I'm looking at the origin now. So which direction am I looking in? I'm at the point negative 1, 2, and I'm looking back at the origin. I kind of need a vector that goes from this point to the origin. That's kind of what I need. I don't need the 3D vector. I don't need the z coordinate. I just need the 2D direction that makes me look from this point, looking at the origin, 0, 0. How can you create a vector that does that? Don't you usually do terminal minus initial? In other words, the 0, 0 is what I'm looking at, minus the point I'm standing on, which is the negative 1, 2. Right, if you're at the point negative 1, 2, and you're looking at the origin, you have to look in the direction positive 1, negative 2. Did that make any sense? It does make sense. The problem is that point negative 1, 2 is back in a different quadrant. Hang on just a second. Look, if I come out here in quadrant 1, and I say I'm at the point 3, 1. So I came out 3 and over 1. To look back at the origin, I need to look back negative 3 and negative 1. I mean, the direction that takes me back there is negative 3 and negative 1. So this makes sense. I'm at the point negative 1, 2. I'm looking at the origin, so I have to look in this direction, 1, negative 2. That's a weird way of asking this question, but it's good. So now I got a vector. But guess what? I need a unit vector. So what's his magnitude? His magnitude is the square root of 5, I think. You agree? So a unit vector here is 1 over the square root of 5, negative 2 over the square root of 5. Cool. Now I got my unit vector. I got my Duf. I'm ready to, same game again. Here we go. It's the same old negative 36 times the x component of this unit vector. plus the 18 times the y component of this unit vector. That's negative 36 over the square root of 5. Oh, look at that, negative 36 over the square root of 5. I'm adding those, they don't cancel out. That is actually negative 72 over the square root of 5. Huh. That's my answer. You can decimalize it. It's approximately negative 20 or 30 something.
Negative 32.2.
Negative 32.2. All right, I'll take that. A lot of good work here. It's really not that long. I'm taking a long time because I explain everything and talk about everything. But I tell you what, for part A, B, and C, by the way, and D, we needed these two things to be accurate. If you would have screwed these up, and people do this on my test, if you screw these up at the beginning, that kind of sucks. I mean, you need these two numbers throughout this problem. You need these two numbers throughout this problem. They better be right. Better be right. Hey. So what was I doing on this one? Hang on. So I had this down. I'm doing pretty good. When I said 4, 7, I was accurate. When I said 150 degrees for part B, I was accurate. Now what's this one? This one's 1, negative 2. The direction is 1, negative 2. Hang on. That's 1, oh, negative 2. That's kind of this direction. Which, by the way, it's not exactly, but sort of opposite this direction. So now listen, what was the 150 degree answer? What was that answer? 40.2. Remember, that was steep. And now part C is asking for this direction, which is almost opposite this direction. Not exactly opposite. If it was exactly opposite, the answer would be negative 40.2. But it's just kind of opposite, which makes it a negative big number. So it kind of makes sense. This direction was 40. Behind me is, exactly behind me is negative 40. But roughly behind me is close to that, I guess. That's cool. I like talking and thinking about being on the surface. Here we go. This is easier, I think. What is the max slope and the direction in which it occurs? The truth is, I think you kind of find the direction first. The direction of max slope is called the gradient. The direction of max slope is called the gradient, and it's this vector. So, and a vector is a good way to give a direction. So the direction is the gradient vector at the point negative 1, 2. And that's a vector made up of those two partial derivatives. It's negative 36, 18. That's the direction of the maximum slope. That's the direction of the maximum slope. Let me just see something. Where is that? That's that's negative 36, 18. You could reduce that. You could call it, because it's just a direction, you could say it's negative 2, 1. That's the same direction as negative 36, 18. Where is that? Negative 36, 18. It's negative 36 on the x, 18 on the y. Hang on. Negative 36 on the x, 18 on the y. Yeah, that's roughly this direction. That's kind of in that 150 degree range. I'll tell you what. It's not exactly 150 degrees, I don't think. But let's calculate the actual maximum slope. So that's the direction of maximum slope, and the actual maximum slope is the magnitude of it. So the max slope is the magnitude of this gradient. And that'll be the square root of, negative 36 squared, 18 squared, some huge number.
40.25 or 25.
Wow, the square root of 1620, right? And then you did that, and you called that approximately 40. I knew it was close to that number, but it's not that. Damn. It's not that number, is it? It's 40.249 Yeah, I don't think you do. I mean, I just think this is damn close. Here, I gotta stop and do this though now. Now you got me thinking. And maybe I'll get you thinking. What, this vector, negative 36, 18. Negative 36, 18. Are you with me? Negative 36, 18, that's not the best picture. Negative 36, 18. I wonder what this angle is. I could do the tangent inverse of y over x. I can do the tangent inverse of negative a half. What does that tell me? Y over x. That's going to give me this vector, I mean this angle, actually, but then I'll add 180 to it. What is this answer? Anybody? Degree mode. What is the tangent inverse of negative a half?
26.6.
26.6. But it's negative 26.6, right? That's in quadrant 4. And add 180 to that, and we'll be in quadrant 2 where we want to be. And I'm saying it's close to 150, but it ain't 150, right? It's, what is it, 100 and...
I got 153.4.
Yeah, you're right. Okay, cool. That's pretty cool. So this maximum slope occurs in this direction. I didn't mean to make you go find the angle. Listen, when someone asks for a direction, you don't have to give them an angle. When they ask for a direction, this is a direction. This is fine. This is a direction. But I wanted to calculate the angle because I knew it was damn close to the 150 and I just wanted to see. Anyway, I wanted to see what it was. You know, I just randomly asked you that question, but when I did, I was close to max slope area there. I was close to the max slope direction. But this is officially the max slope direction, and this is the max slope. Cool. So I stand on this surface, I stand on this point, and I can calculate slopes in all these different directions. And the direction doesn't go up or down. The direction is a 2D direction. It just gives me a direction to look in. But when I think about the slopes, then I kind of like to look up and down. I mean, when the slope's positive, I'm going, holy shit, that's a steep slope, and now it's coming down, now it's coming down, now, oh wow, now it's down, now it's a negative slope, now it's a steep slope again, you know, so I'm using my arm to indicate what the slope's doing. But I'm just looking in this two-dimensional direction given by the unit vector u. That was cool. That was good. That was good. I think I'll get rid of all that. You guys got any questions? Okay, it's good stuff. This is 13.6, the Duf and the Gradient. There's another idea about this gradient. This gradient's kind of interesting. It turns out that it points in the direction of maximum slope. I don't know how to say this or convince you of it. I'm just going to say it, I think. Then it turns out that the gradient vector is normal. Do you know what normal means?
Perpendicular.
Yeah, good, perpendicular. It's normal to the level curves. It's normal to the level curves of the function. Now, let's just believe that. We need to know that. We need to believe it. We can try to talk about it and think about it. I'd rather sort of do a problem. Let me see what I want to do here. Yeah, let me just do this one, 48. So I'm in 13.6 and I'm looking at problem 48. And here's what they do. They give me this. Give me this surface. It's a nice, easy one this time, instead of being so complicated. I'll tell you what, they gave me that surface. They say that C is 25. Now, and they want me to sketch a level curve. There's a lot going on here, but let's sketch a level curve. So if you remember, this was from 13.1. I don't know how far you've gotten yet, but in 13.1 we were sketching level curves. If you remember, we would take this C value, we would put it in for this Z value, and we would sketch the resulting curve we get. And what do I get? I get a circle of radius 5. So this is a 3D surface, but I'm looking at a 2D image of just where Z is 25. Z or C is 25. This C, it's a Z value. I plugged it in for Z. And when Z is 25, I get this circle of radius 5. And we label it C equals 5. Or no, C equals 25. Sorry, it's radius 5, but C equals 25. We could do another level curve just to see what's going on, but I'll, that's good enough. That's that level curve. You know, let me tell you something. Okay, let me say a couple things. You know, we sketched level curves a couple days back, you know, and if I sketch some level curves that look like this, now, is that a hill or a valley? And you would say, no. You would say, you don't know. See, I ask you these tricky questions. Is that a hill or a valley? And you don't know until the labels are put on there. See, now if I call this C equals 25, C equals 20, C equals 10, C equals 5, now that means the C values are getting less toward the interior. Those C values are Z values, which are heights. So the heights are getting less in here. This must be a bowl or a valley. Right. As opposed to the same thing where I call this C equals 25, C equals 10, C equals 5. Now the higher values are interior here, and so those are the higher elevations, and this would be the top of a mountain here, I guess. The C values are Z values, and they can be thought of as elevations or heights. If you, all right. So is this a hill or a valley? Okay. Now we know that's a valley. That's a hill. And so if I wanted, let me think here now. If I had a gradient for this, and I was trying to draw a gradient, it would point to the gradient points in the direction of maximum slope. Now wait a minute. Would that be toward this? Let's see. I think that would be this way. Because isn't it getting steeper the further out I go? I mean, the direction of maximum slope would be away from the valley. You don't want to point down toward the valley. That would be the direction of minimum slope, perhaps. The direction of maximum slope would be where the Z values are increasing, which would be out. What about on this one? I think on this one, the peak of the mountain is here. I think the gradient vector would point in the direction of maximum slope. I think it would point toward the interior here. I just made this statement without really convincing you of it, that the gradient vector is normal to the level curve. So when you saw me trying to draw it, I was trying to draw them perpendicular or perpendicular to the tangent line. Are you following me there? I was trying to draw these normal vectors perpendicular to the curve. All right, so hang on. So now listen, here we are. Back to this again. So let's say I'm walking around this C equals 25. Let's just say I'm hanging around this thing. Now, what do I do if I want to, okay, so what do I do if I want to get higher? If I want to get higher, according to the labels, what do I do?
Go out.
Go out. Okay. What if I want to get lower?
Go inward.
Go in. What if I want to remain at my current elevation?
Just go along.
Stay on the curve. That's what a level curve is. It's a constant elevation of 25. It's a constant, if you walk along this curve, then you remain at a C value or a Z value of 25. So the direction to head in would be this tangent vector, head off in that direction. But the truth is, as soon as you take a few steps, please stay on the path. Try to, right. If you want to remain at your current elevation, you remain on this curve. So wait a minute, if you're remaining at your current elevation, then what's your slope? If I'm walking along this curve and I'm not changing elevation, I don't mean to walk like such a jerk, but if I'm walking along this curve and I'm not changing elevation, then what's my slope? I mean, if I'm not rising or falling, what's my slope? I think my slope is sort of 0 off in this direction. Yeah. Wow, all right. All right, so this is a long discussion, but I think what I'm trying to tell you is, I'm trying to sort of convince you of this statement, and I think maybe I have, because you're following me. What I'm trying to say is, when you're on a level curve and you head off into these directions, you're heading off in a slope of 0. You're remaining at your current elevation. And so to radically change your elevation, you head off perpendicular to that. And in this one, away from that is a growing elevation. So that would be the gradient, pointing in that direction. And this direction would be the opposite of the gradient, the negative gradient, the negative of the gradient. Sorry for my little sloppy notes, but this one would be the opposite of the gradient, heading in interior to that, opposite that. So now it kind of makes sense that maybe the gradient should be perpendicular to the normal curves. If the normal curves have a slope of 0, and the maximum slope would be perpendicular to that, I guess. Perpendicular to the normal curves. They wanted me, all I did so far was sketch a level curve. But they said that you're at the point 3, 4. By the way, if you're at the point 3, 4, 3 squared plus 4 squared is 25. So if you're at the point 3, 4, you are on this level curve. You're on this level curve right there at the point 3, 4. And they wanted me to calculate the gradient at that point. So let's do the gradient. First of all, the gradient in general is a vector. In general, at any xy, it's a vector. And here's what it is. It's the partial derivative with respect to x. 2x, comma, the partial derivative with respect to y, 2y. That's the gradient for this surface. At this point, let's calculate it. Plug in the 3 and the 4 for x and y. And the gradient vector at the point 3, 4 is 6, 8, I guess. 6, 8. And if I drew that vector at this point, I would go, I went over 3 and up 4. I'm trying to draw an accurate picture. It may not be too accurate. Now I'm going to try to go over 6 and up 8. And draw that vector. This is a picture of the gradient vector at this point. And does it look like it's perpendicular to the normal curves? Sorry. Does it? I said the wrong words. Does it look like it's normal to the level curves? It sure does. It looks like it is normal to the level curves. That was 48. What did it say? Find a normal vector to the level curve. You know, they didn't say find the gradient, but when they say find a normal vector to the level curve, that was the gradient. At the point, and then I guess I added all this illustration. They didn't say to illustrate all this, I did that. I guess you could have just done this work. There's the answer. But in the past, I have asked you to illustrate all this. I like you to make the connection. I like you to draw the level curve. I like you to find the gradient. I like you to draw it all and see that it's perpendicular. So I like that. Well, I think we're at the end of class today. So I didn't really push ahead at all. I actually reviewed some of Monday's ideas, but I did add this topic. This gradient is normal to the level curves. I didn't get to that Monday, so that was new today. But I wanted to stop and digest this a little. I think maybe I'll push ahead Friday. We also should think about a quiz.